This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing electrical analogy for combined modes of heat transfer in a heat and mass transfer subject. Heat transfer is by the conduction process. The mathematical formula for the heat transfer by the conduction process is written as Q is equal to minus of Ka dt minus dx, where Q is representing the heat flow, that is the magnitude of heat energy that is transferring. Here K is representing thermal conductivity of the material. It is a property of the materials. A is the area of the cross section. dt is the temperature difference. dx is representing the thickness of the slab or thickness of the block. Here dt by dx is also called temperature gradient. It is always represented in negative. Hence Q is equal to minus of Ka dt by dx. These equations, it can be represented as Q is equal to Ka T1 minus T2 divided by L. After integrating these equations for the temperatures T1 to T2 in a length of L, it can be modified as Q is equal to K into A into T1 minus T2 divided by L. These equations, it can be written as T1 minus T2 divided by L divided by Ka. This is known as equation number 2 now. Here L by Ka, this term is known as thermal resistance for the conduction process. Here an electrical analogy is useful as a concept in solving conduction problems, and general, it is related to the general heat transfer problems. Here when comparing with the current flowing through a conductor, assume initially it is having V1 is the voltage and Vt is the voltage at the other end now. Because of voltage difference between the conductor, that current is flowing one point to another. Let R be the resistance offered by the conductor now. I is the conductor. I is the current flowing. So by using this equation, we can write it now. Here I equal to V by R now, where V is representing that is the change in voltage now divided by electrical resistance. When comparing these equations with the transfer of heat energy by using conduction process, it can be represented as T1 is the initial temperature, T2 is the final temperature. Here L by Ka is representing thermal resistance for the conduction process, and Q is the energy that is flowing through heat now. It is similar now. Q is equivalent to I current now. Here T1 and T2, these are called thermal potential. Similarly, V1 and V2 is the electrical potential is there now. So this equation, it can be written as Q is equal to, we can write it now, that is T1 minus T2 divided by here R. R is equal to L by K here now. Hence L by K is treated as thermal resistance for the conduction process. Here the amount of heat energy that is flowing in a conductor generally determined by using Fourier's laws of heat conductions. It is given by, already I told, it is equal to minus Ka dt by dx. Generally the Q is representing in watts, so A is in meters, dt is representing the temperature difference. Generally it is measured in degree of Kelvin or degree of centigrade, and thermal conductivity equal to watts per meter per degree Kelvin. Here I am taking a composite walls here now. Here in this process, the wall having this thickness is equal to L now. T1 is representing the temperature at inside of the wall, where it is having contact with the hot fluid, and T2 is representing the other end of the wall, which is having in contact with the fluid which is having at lower temperature. Here in this process, the heat energy from the hot fluid is transferred to the surface, inlet surface, which is represented here as 1. Assume T here, alpha is representing that the temperature of the hot fluid now, which is greater than T1. The heat energy flowing from hot fluid to T1 here now by using convection process. From T1 to T2, that is within the metals, the conduction process taking place. From T2 to again ambient air, that is environment, it flows through convection process. So T2 to again TA is representing the air temperature. So in this mode of heat transfer, first convection process is taking place to transfer the energy from hot fluid to the surface. After that, within the conductor conduction process, again from conduction to air, that is again convection process. So the total energy which is flowing from T alpha to TA, this is the temperature difference, is given by the equation. So T alpha minus TA divided by 1 by HIA, that is at inlet temperature hot fluid, where HI is representing the coefficient of convection for hot fluid, A is the area, surface area, plus L by Ka, where L is equal to length, K is the thermal conductivity, area again now, surface area, plus 1 by H naught A now. This 1 by HIA, it is known as thermal resistance offered by the convection process between hot fluid to the inner surface of the block. L by Ka is known as conduction resistance, plus 1 by H naught A is called here convection resistance between the surface which is having temperature T2 to the atmospheric air now. So according to the circuit diagram, electrical circuit diagram, it can be measured, represented as T alpha to TA, the energy is flowing now. So here the resistance 1 is there now, I divided 1 by divided by H1A, that is the resistance of convection, and the temperature at the contact of hot fluid to the surface is represented T1. Again T1 to T2, that energy is flowing by using conduction process. Afterwards from T2 to TA, that is the outer surface of the solid to the atmosphere, again convection process, having resistance is equal to 1 by H naught to A naught. The composite slab or the wall now. Here in previous problems we have taken only one block which is having in contact with the hot fluid as well as the cold fluid. But in this case composite slab, the thickness of the wall or the slab is made up of different types of materials. Here according to the problems we have taken just 3 different materials which are represented here 1, 2 and 3, having same area of cross sections with the different thermal conductivities. Let T alpha is representing the temperature of the hot fluid which is in contact with the surface having temperature T1, or that means inlet temperature, inlet surface of the block 1, and the heat energy flowing from T1 to T2, where T2 is representing the interface of first block and second block, having thickness is equal to L1. The heat energy flowing by using conduction process. From T2 to again T3 is there now. So conduction process is taking because of it is a solid. From T3 to T4 again conduction process. That means from these problems T1 to T2, T2 to T3, T3 to T4, the heat energy is flowing within the different blocks of composite wall by using conduction process only. From T4 to TA, the convection process taking place. So here writing, since it is steady state conditions now, that is the amount of heat energy that is flowing in each section for unit time, it is remains constant now. Hence for the first one, that is T alpha to first surface is given by convection process, Q is equal to HI into A into TF minus T1, or Q is equal to HI into TF minus T1. For the second one, conduction process, so Q is equal to K1 into A into T1 minus T2 divided by L. By using this relation, so Q divided by K1 A divided by L1 is equal to T1 minus T2. Similarly, from second block to third block now, Q is equal to K2 into A T2 minus 3 divided by L2. It can be written as Q by L2A divided by L2 is equal to T1 minus T3. Heat transfer from the secondary interface to the outer surface of the composite wall is given. Q is equal to K3 into A into T3 minus T4 divided by L3. It can be written as Q divided by K3A divided by L3 equal to T3 minus T4. From outer surface to atmospheric air is given by Q is equal to H0A T4 minus TA. It can be written as Q divided by H0A is equal to T4 minus Tn. So combining this all the equations, that is left hand side this one, right hand side other one. Now we got to towards the right side Tf minus T1 plus T1 minus T2 plus T2 minus T3 plus T3 minus T4 plus T4 minus Ta. Here plus or minus all are get cancelled now. Finally we are having Tf minus Ta towards the right side. Here if Q is the common, A is also common. If you take this is nothing but we can take it as Q is the common 1 by HIA plus 1 by K1 A divided by L1 plus 1 by K2 A divided by L2 plus 1 by K3 divided by K3 A divided by L3 plus 1 by H0 A. It is equal to Tf minus Ta. So from this relationship, Q is equal to Tf minus Ta divided by 1 by HIA plus 1 by K1 A divided by L, 1 by K2 A divided by L2, 1 by K3 A divided by L3 plus 1 by H0 divided by A now. These are nothing but here now 1 by H1A, it is known as thermal resistance offered by the convection process. Second conduction process, conduction process, conduction process and conduction process. So it can be written as Q is equal to Tf minus Ta divided by 1 by A into 1 by Hi plus 1 by H0 and sigma of N is equal to 1 to N is equal to N, that is L1 divided by Kn. This is the general equation for the heat energy flowing from the hot fluid to the cold fluid through the number of slabs of a composite wall. These equations, it can be represented as an electrical circuit the way here it is equal to Tt, here T1, here resistance is equal to 1 by H1A1, L1 by K1 H1 like this now. So heat energy is flowing now. So the heat energy which is flowing from hot fluid to cold fluid, it is similar to the electrical current which is flowing from higher voltage to lower voltage with the different resistance having is in between. Okay, based on this content, one problem is a slab of 0.2 meters mm thick with a thermal conductivity of 45 watts per meter Kelvin. This is heat a furnace at 500 degree Kelvin, both by convection and radiation process. The convection coefficient has a value of 50 watts per meter square per degree Kelvin. The surface temperature is 400 Kelvin on this side. The heat is transferred to the surroundings at T alpha to both the conduction as well as the radiation process. The convection coefficient on this side being 60 watts per meter square per degree Kelvin. Determine the surrounding temperature. Assume F is equal to 1 for radiation. The thickness of the slab is equal to, here given L, which is equal to 0.2 meters. Thermal conductivity of the wall is equal to K is equal to 45 kilowatts per meter per degree Kelvin. Furnace temperature is given here 500 here now. That means here T alpha 1 is equal to given 500 degree centigrade now. And H is equal to, that is 50 watts per meter square per degree Kelvin. The surface temperature, that is here T1 is equal to 400 degree Kelvin. Conversion of coefficient 60 watts per meter square at other side. Shape factor is given F is equal to 1. So let the surface temperature at the outlet be T2. At this we have to determine. And also T alpha 2, that is the air temperature. The surface area here is not given. Assume it is equal to 1 meter square now. Since it is a steady state condition now, that is the amount of heat energy flowing through each section is remains constant. And first of all, we are taking the amount of heat energy which is flowing furnace to the surface which is having temperature T1. That is the air between these two now. Here the heat energy is flowing from the furnace to the surface of the block by using only convection as well as the radiation process. Hence the total energy is the sum of the heat energy that is transferred by convection as well as the radiation. From this relations we have, for radiations, F into sigma into A, it is given T alpha 1 to the power of 4 minus T1 to the power of 4 plus H into T alpha minus T1 now. Where F is equal to 1, again A is also equal to 1, and T alpha 1 is equal to, it is given 500, but it should be converted into degree Kelvin. The problem number 2, the walls of heating unit in the cold region comprise 3 layers 10 centimeters outer brick work. K is equal to 0.75 watts per meter per degree. 1.5 centimeters inner wooden paneling having K is equal to 0.75 watts per meter per degree. 8 centimeter intermediate layer of insulating materials. The insulation layer is stated to offer resistance twice the thermal resistance of the brickwork. If the inside and outside temperature of the composite wall are 30 degrees centigrade and minus 10 degrees centigrade respectively, determine the rate of heat loss per unit area of the wall and thermal conductivity of the insulating materials. So the thermal resistance of for the plane wall of thickness delta, area A, thermal conductivity K is prescribed by the relations RT is equal to delta divided by K A now. So according to this relationship, the thermal energy which is flowing is given by the equations Tg minus Ta is equal to L1 divided by Ka plus L2 divided by Kbab plus L3 divided by Rkc AC. First we are determining the resistance of the brick equal to RT1 is equal to, it can be taken as now here R is equal to K divided by A into L now, which is equal to, here RC is equal to 10 into 10 to the power of minus 2 divided by 0.275 into 1, which is equal to 0.133 degree per watts now. Similarly, the resistance of the wooden paneling is equal to RT1 is equal to 1.5 into 10 to the power of minus 2 divided by 0.133 into 1, which is equal to 0.1128 degree per watts now. The insulating materials is equal to here 2 into 0.113, because the resistance of the brick here the given work is given now 0.13, but insulating material is twice is given, hence we are taken its value is the twice value. The total resistance is equal to RT is equal to sigma of RT. It can be values is equal to 0.1133, 0.1128 plus 0.2266, total is equal to 0.5118 degree per watts now. Heat loss is equal to, you can take it as delta T divided by sigma of RT. So it is equal to delta T is representing that is different temperature difference from initial to final. So initial 30 degrees to final is minus 10 is required. Minus of minus 10 divided by RT, that is the total resistance, is equal to this value, which is equal to 78.115 watts now. So the thermal conductivity of the insulating material is equal to, you can take as K is equal to delta divided by ART. From this relationship we got 7.5 into 10 to the power of minus 2 divided by 1 into 0.51182, which is equal to 0.1465 watts per meter. A furnace wall is made up of steel plate 10 mm thick, that is K is equal to 62.8 meter hour per degree, lined on inside with the silica brick 150 mm thick. K is equal to here 7.3 kilojoules per meter per degree centigrade, and on the outside of the magnesium brick 200 mm thick. K is equal to 18.84 kilojoules per meter per degree centigrade. The inside and outside surfaces of the walls are temperature 650 degrees centigrade respectively. Make calculations for the heat loss from unit area of the wall. It is required that the heat loss be reduced to 10 megajoules per hour by means of air gap between the steel and magnesium bricks. Estimate the necessary width of air gap if the thermal conductivity is 0.126 kilojoules per meter per hour per degree centigrade now. The thermal resistance for a plane wall of thickness delta, area A, and thermal conductivity K is prescribed by the relations RT is equal to delta divided by Ka. So here the circuit diagrams, the electrical analogy for the thermal conduction process, it can be represented as here T1, T2, T3 and T4 and so on. The thermal conductivity is equal to L1 divided by K1 A1, L2 divided by K2 A2, L3 divided by K3 A3 now. Okay, resistance of the steel plate is equal to, it is given by 0.01 divided by 62.8 into 1, which is equal to 0.000159 degrees hour per Kelvin now. Similarly, the silica bricks RTT is equal to 0.15 divided by 7.32 multiplied by 1, which is equal to 0.02049 degree hour Kelvin. Resistance for the magnesium bricks is equal to RTS is equal to 0.20 divided by 18.84 multiplied by 1, which is equal to 0.01061 degree hour per Kelvin now. The total resistance of the composite wall is equal to sigma of RT is equal to sum of the resistance of RT1 plus RT2 plus RT3, which is equal to 0.03126 degree hour per Kelvin. A slab of 0.2 mm thick with thermal conductivity of 45 watts per meter Kelvin receives heat from the furnace 500 K both by convection and radiations. The convection coefficient has a value of 50 watts per meter square per degree Kelvin. The surface temperature is 400 Kelvin on this side. The heat is transferred to the surroundings at T alpha 2, both the convection as well as the radiation. The convection coefficient on this side being 60 watts per meter square per degree Kelvin. Determine the surrounding temperatures. Assume F is equal to 1 for the radiations. Here consider the area of the cross section is equal to 1 meter square and sigma is equal to, that is Stephen Boltzmann constant is equal to 5.62 into 10 to the power of minus 8 now. So heat received is equal to by both radiation as well as the convection process equal to Q is equal to F into sigma into A into T alpha to the power of 4 to T2 T1 to the power of 4 plus HA into T alpha minus T alpha 2 now. By using this relationship we got to here now 1.567 into 10 to the power of minus 8 but on doing the calculations, we kept that 100 just inside the bracket into 500 divided by 100 to the power of 4 minus of 400 divided by 100 to the power of 4 plus 50 into 1 into 500 minus here 400, which is equal to 7092.2 watts. For determination of T2, it is equal to Q is equal to delta T by R now. By using the relationship, we got delta T is equal to QR, which is equal to 7092.2 into 0.2 divided by 45, which is equal to 31.57 Kelvin. So T2 is equal to 400 minus 31.57 is equal to 368.43 now. On the other side, that is heat received is equal to, here Q is equal to, again same F into sigma A into T2 to the power of 4 minus T alpha to the power of 4 plus HA into T2 minus T alpha 2. Here the temperature, it is given 368.43 already we measured, determined. T alpha 2 we have to determine these values now. So 1.567 into, here it is similar to the previous case that 100 10 to the power of minus 8 is brought inside the bracket, now. That is 368.43 divided by 100 to the power of 4 minus of T alpha 2 divided by 100 to the power of 4 plus for the conversion process 60 into 1 368.43 minus T alpha 2, which is equal to 5.67 T alpha to the power of 4 plus 6 alpha 2, which is equal to 16056 now. On doing this trial method, we can determine the value of temperature T alpha 2 is equal to 263.3 degree Kelvin. Okay, these are the textbooks that the reference are followed for the collection of materials. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.